Warm greetings to everybody and welcome to my presentation. My name is PRATHOSHINI Devi and I am currently doing my third year in MSc Software Systems. I will walk you through my approach to solving this problem of symmetry check in a binary tree, which involves using a combination of tree traversal and symmetry checks. The problem statement we are addressing involves checking if a binary tree is symmetric or not. We are given an integer n representing the number of nodes and an array that represents the level order traversal of a binary tree. The array may contain -1, which represents null nodes. Our task is to determine whether the binary tree is symmetric, meaning if its left and right subtrees are mirror images of each other, and to print whether the tree is symmetric or not. We have to print the level order traversal of the tree along with it. Our objective is to implement an efficient algorithm that checks if a binary tree is symmetric. This problem touches upon important concepts in data structures, specifically binary tree construction, symmetry checking, and traversal techniques. These concepts are fundamental in software engineering, particularly in solving complex problems involving hierarchical data structures. Before diving into the solution, let's quickly recap what a binary tree is. A binary tree is a hierarchical data structure where each node can have at most two children, referred to as the left child and the right child. This structure is critical in various computer science applications such as searching algorithms, database indexing, and parsing expressions. Here's a visual representation of a binary tree with nodes 10, 5, 20 and their respective children. Coming to the code, let's begin by looking at how we define the structure of each node in our binary tree. In this code, a node is represented by a struct named node. Each node has three components: data, left, and right. Data is the value which is stored inside the node, left is the pointer to the left child node, and right is the pointer to the right child node. When we create a new node, the constructor initializes the data with a provided value and sets both left and right to null pointer, meaning the node starts with no children. This is important because it allows us to add child nodes later during the tree construction process. Now let's move on to the tree construction part. To build the binary tree, we use a function called insert. This function takes two parameters, an array which represents the level order traversal of the tree and the size of that array n. The process starts by checking if the array is empty or if the root node is a null value represented by -1. If so, it returns a null pointer, otherwise it creates the root node using the first value in the array. To correctly place each subsequent node, we use a queue data structure. The root node is pushed into the queue and from there, we iterate through the array, adding left and right children to each node until the entire tree is constructed. Let's dive deeper into the role of queue in this process. Once the root is added to the queue, we go through the array, processing each node in a level order manner. For each node we pull out of the queue, we check if it has a left or right child in the array. If a value which is valid other than -1 exists, we create a new node and set it as the left or right child of the current node. We then push these newly created nodes into the queue, ensuring that they will be processed in the subsequent steps. This process continues until all nodes from the input array are processed and placed correctly in the binary tree. Now that we have built the binary tree, let's discuss how we check if it is symmetric. The is-symmetric function is key here. Symmetry means the left and right subtrees are mirror images of each other. The function begins by checking if the root node is null. If the tree is empty or has only one node, it is automatically considered symmetric. Otherwise, we use a breadth-first search approach to compare the left and right subtrees at every level. We enqueue the left and right children of the root and begin comparing nodes. At each step, we check if both nodes are null or if one is null while the other is not. If both are null, we move on to the next pair of nodes. If one is null but the other isn't, the tree is not symmetric. We continue this process for all nodes, ensuring that corresponding left and right nodes mirror each other. If any discrepancy is found, the function immediately returns false, indicating the tree is not symmetric. Within the is-symmetric function, we handle each level of the tree by checking pair of nodes. First, we compare the left child of the left node with the right child of the right node. Then we compare the right child of the left node with the left child of the right node. If any of these comparisons fail, we can safely conclude the tree isn't symmetric. If all comparisons hold true for every node, then the function returns true, confirming that the binary tree is symmetric. Finally, let's look at the main function that ties everything together. Here we accept the number of nodes n and their values as input from the user. These values are stored in an array which is then passed to the insert function to construct the binary tree. Once the tree is constructed, we use the isSymmetric function to determine whether a tree is symmetric. Based on the result, we print either the tree is symmetric or the binary tree is not symmetric. Additionally, we print the level order traversal of the binary tree excluding any -1 values. To give you an overview of the algorithm, we start by constructing the binary tree using level order traversal. A queue is employed to ensure the nodes are added to the correct positions. Next, we perform a symmetry check using an iterative breadth-first search approach. We compare nodes at each level to verify if they are symmetric. The output includes whether the tree is symmetric or not, followed by the level order traversal of the tree. An essential part of the solution is the queue data structure. A queue follows the first in, first out principle, which is perfect for level order traversal. In our case, we use the queue to insert and compare nodes at each level. Queue operations include enqueue, which uses the push function, dequeue, which uses the pop function, and checking if the queue is empty using the empty function. This ensures that we process each level of the tree correctly. The BFS algorithm is at the heart of our solution. We initialize the queue with a root node and then we process each level of the tree, adding its children to the queue until the entire tree has been traversed. BFS ensures that we can check symmetry by comparing corresponding nodes in the left and right subtrees at each level. Here is an example test case. For the input array 1, 2, 3, -1, 4, 5, -1, we construct the binary tree shown. The resulting tree has 1 as the root with 2 and 3 as its children and further nodes in the subtrees. After checking, the tree is found to be symmetric. In this example, the given input array creates a balanced binary tree. Since the left and right subtrees are mirror images of each other, the tree is symmetric. This is a more complex case where all nodes are filled, making it an excellent example of symmetry. In the following custom test cases, both the binary trees are considered asymmetric as the left and right subtrees are not mirror images of each other. The time complexity of our solution is big O of n, where n is the number of nodes in the binary tree. This is because we traverse each node exactly once during the construction and the symmetry check. The space complexity is also big O of n as we store the nodes in a queue for processing. Thank you for watching this presentation.